Hello friends, welcome to Mechanical Engineering online classes. Today's lecture will be delivered by Miss Shravani Sriramoju.
So as the name suggests, queuing model or queuing problem, this is identify the presence of a group of customers who will arrive randomly to receive some service. So for example, there is a service facility here with several servers. So server number 1, 2 and so on. Many servers are there. Now the customers will arrive to take some service, and if the number of servers is less, then comes the concept of a queue. They will all form a queue, and these customers will go to several different servers. So this queue is also called as a waiting line. So this is the service facility, and after receiving the service, the customers are leaving the service station. So they are the leaving customers. So this is the arriving customers. Customers are arriving here. So this entire thing, starting from the customer arrival to the service being completed, this entire thing is the system. This is called a system. So queuing is nothing but a congestion phenomena. So why are we discussing this? The customer is coming, they are forming queues, they are getting served, and then they are leaving. The question here is, not everything is as simple as it simply appears. We are just drawing a diagram. The scenario will not be this simple. The customer upon arrival may be attended to immediately, or the customer may have to wait until the server is free. So the service time that is required to serve a particular customer is a statistical variable. So this is a major problem which has to be dealt very sensitively in many areas, like in the field of business like banks, booking counters, or in industries where servicing of machines is an issue, or in government offices it might be the railway counters or post office counters, or when it comes to transportation department it might be at the airport or the harbor. And in everyday life we may have to wait at the elevators or restaurants to have to get a table free, or even at the doctor's chamber we have to wait. So the queuing models are basically relevant to service oriented organizations, so that we may have to suggest ways and several means to improve the efficiency of the service. So how do we improve the efficiency of the service? As a customer, if we think, the customer will want the service to be provided as and when the customer arrives. So that will be the demand or need of a customer. Now what can the industry or organization do in such cases? One idea is increase the number of servers. Server means you have to increase the number of people working. So the staff is increasing. So the idea is to increase the number of employees. What will happen with this idea if at all we are to implement this? The immediate consequence is that the cost is highly increasing, because the number of employees increase, the salaries and all other things, that is increased. And one another thing is, every time the customers will not be in the same, the queue is not always the same every time. So there are always some down times and up times. So suppose you are waiting at the bakery during your say New Year. So the queue line is different than you go in some other ordinary days. So customers, or the number of customers, or the number of queues, or the service times, they are all variables. So if at all we are increasing the number of employees or servers just based on some peak hours or peak days, rest all days when the business is down, when the demand is low, that time these employees and the servers are idle. So utilization of employees and the servers is reduced. So that is also another cost. So you are increasing cost only for few days. Only for the sake of few days you are increasing the cost for the entire year. So that is not a good idea. And not just that, it is also very unrealistic to assume that a large scale increase in the staff is possible in an organization. Every organization is fit only to to a particular amount of staff or machines or whatever. We cannot expect the organization to increase its staff or other facilities drastically. So queuing methodology indicates the optimal usage of existing manpower and other resources to improve the service. So that is a realistic approach. So the relationship between queuing and service rates can be diagrammatically illustrated using cost curves. So if time is taken as datum and cost is dependent on time, which is mentioned on y-axis, then the cost of service is directly proportional to the time. So quicker it comes with the cost of queuing. At a slow service rate, the queues will build up. The cost of queuing will increase that time. And the cost of waiting may be represented as this. This is the cost of waiting. This is the cost of service. So an ideal service unit will always minimize the operating cost of the entire system. It comes somewhere between the two, like this. So this is the cost of operation. The system. So this graph is the cost structure of a queuing problem. So now let us see the elements of a queuing system or the structure of a queuing system, or otherwise they all form the characteristics of a queuing system. So let us see the characteristics of a queuing model or a queuing system. So a queuing system can be described by the following components. The first one is the arrival or input, or we can call it as an inter-arrival distribution also. So this represents the pattern in which the number of customers will arrive at the service facility, or it is a statistical pattern of the arrival that is indicated by a probability distribution of the number of arrivals in an interval. So this is a discrete random variable. This will be a discrete random variable. So customers are different people coming randomly. So that's a discrete random variable. The arrivals may also be represented by the inter-arrival time. Inter-arrival time means period between two successive arrivals. So alternatively, the probability distribution of the time between successive arrivals also can be studied to ascertain the stochastic aspect of the problem. So time between successive arrivals is the inter-arrival time. So why are we calling it a stochastic problem is because stochastic means probabilistic. So we can only say that probably this may happen, probably that may happen. Based on the past data, based on the previous experiences, we'll find how the pattern is distributed mathematically. Then we'll generate a mathematical model and try to analyze what will happen now if I implement so and so facility or so and so readiness. If I am ready with this, will I meet the demand, or will the supply be more, or will the demand be more? So it is based on the probability. Today I am setting up a shop. I do not know tomorrow how many customers are coming, but still I will be ready with some amount of the material, raw material. Based on what I should be ready with raw material, how much should I have the raw material? It should be based on some previous experience. So this is a probability. Okay, probably these many number of customers may come for these many items. So this is a probabilistic approach. So that's the reason we are calling it as to ascertain the stochastic aspect of the problem. Means we do not know how many customers are going to come today or tomorrow or any day for that matter. So we call it a stochastic aspect. If we exactly know how many are coming, like for example, if I know that I have to do these many jobs today, I know it. That is a deterministic problem. Probabilistic and deterministic are two different things. So this is a probabilistic problem. Alright. And so we said that we may find the probability distribution of the number of arrivals in a particular interval, or we may check with the time interval between the successive arrivals. So using any of these, we can try to assess the stochastic aspect of the problem. So this is the first element of a characteristic that will define a queuing model. So arrival rate is nothing but the number of customers arriving per unit time. So in case we are using the inter-arrival time as our first element, which is the input element or the arrival element. So that inter-arrival time is a continuous variable. It's continuous the variable is continuous in nature. So as said, the probability distribution of the arrival pattern can be identified through analyzing the past data. So the discrete random variable, that is indicating the number of arrivals in a time interval, and the continuous random variable, that is indicating the time between two successive arrivals, that is the inter-arrival time, they are interrelated. Alright, so if the number of arrivals is following a Poisson distribution, then the corresponding inter-arrival time will follow an exponential distribution. So this property is used in order to derive to elegant results on any queuing problem in general. So the mean value of arrival rate is denoted as lambda. So now let us see the second element, which is the server or service, called the departure distribution. So this will represent the pattern in which the number of customers are leaving the service facility. The service may be offered through a single server like a ticket counter, or through several channels like as a train arrives in station with several platforms. So there are many doors. So sometimes the service is to be carried out sequentially through several phases, like for example, if you are going to board an airplane, then you may have to pass by several checking counters. So there's only one customer, but there are many service facilities, many service stations that you have to pass by. So that is called as a multi-phase service. Or otherwise in government offices, the papers or files, they will move through number of phases in terms of the official hierarchy until they arrive at the appropriate level where a decision can be taken. So the departure distribution is another important characteristic to understand the queuing model. So here the departures may be just like in our first element. We can consider two variables, so service time or the inter-departure time, means the time between two successive services, like inter-arrival in the first element. Like that, here we can consider inter-departure time, which is the time between two successive services. So like arrival time, the service time may be constant or variable, but it is known or random, means a variable with only known probability. So if service times are randomly distributed, then we have to find what probability distribution will best describe the behavior of service. So generally an exponential probability distribution is used to describe the service distribution. So mostly this is what is applied for a service element. And service rate is nothing but the rate at which one service channel can perform the service, or otherwise it is the number of customers served per unit time. And we pick the exponential distribution mostly because this service rate here assumes that the service channel is always busy, means no server is idle. There is no concept of idle time. So no idle time is allowed. It assumes that the service channel is always busy and is always serving the customer. There is no idle time. And the mean value of service rate is denoted as mu. And because we have designed the system or organization in a way to serve the customer properly, we have more grip on serving. So the service rates are more uniform than the arrival rate, because the customer is not in your hand but the service is in your hand. So you can see that the service rates are uniform. Arrival rates may or may not be uniform. That is not in our hands. So service rates are more uniform than the arrival rates. Now let us see the service channels. Service channels may be single or multi-channel. And the queues, the queue may be a one line or parallel lines, which we just discussed in our element 2, or they may be in series. Series means the example of airport, or it may be a complex combination of both. So parallel line means one line means it might be an ATM. So there is only one ATM, or there is only one queue. Parallel means, for example, where customers are served simultaneously. As an example, barber shop. So there will be many barbers. And series means a customer is successively passing through several channels before service is completed. So that is a multi-phase. The example that we have taken is the airport check-in, or otherwise a product that need to go to several machines before it is completely produced. Any product. Let us see the fourth element, which is the service discipline. Service discipline is nothing but the order of service. This is nothing but a rule by which the customers are selected from the queue for the service. Now for example, there's an ATM machine, people are going. The first person who goes will first get the service and that person will first come out. So there is a first come, first serve. First come, first served is one condition, one rule, which we just abbreviated as FCFS. First come, first served. If you come first, you get served first. Or there is another way. Like for example, you are filling your bag with several books. There are several boxes. I kept a box first, then I kept second box, then I kept the third box. Here I am going to zip it. Now when I want to remove them, the first which went inside is first. That will come last. So last whatever had gone inside is number 3. So that will come first. So that is called as last come, first served, or LCFS, simply abbreviated like that. Or it may be random, or it may be based on some other priority. So these are several service disciplines or orders of service. So sometimes the queue discipline does not always take into account the order of arrival. So the server will sometimes choose one of the customers to offer service at random. So such a system is known as service in random order. So random, this can be abbreviated as 0. Service in random order. So the example may be like while allotting an item with high demand and limited supply. The demand is high and supply is very limited. Like for example, a test match ticket, or a share of public limited company. There the supply is limited but the demand is very high. That time zero system is the only possible way of offering service. When it is not possible to identify the order of arrival, many orders come, many orders arrive at a time, so they are randomly chosen. So that is one kind of service discipline. This is the fourth element. Let us see the fifth element. Fifth element is the maximum number of customers that are allowed into the system. So we may allow finite number or we may allow an infinite number. Infinite means there is no limit to it, where we cannot specify any limit. Finite means, now for example, you are going to watch a movie in a theater. The maximum number of customers allowed is finite. The number of chairs is finite. But if you are talking about a polling booth, or if we talk about the polio booth, so the maximum number of customers, you cannot say that okay, we have given to 100, will not give for the rest. No, so there it comes out to be infinite. Any number of people may come and they will be served. So that is the infinite. So this is the fifth element or characteristics of a queuing model to define a queuing model. Then the sixth one is the calling source or the population. So the arrival pattern will depend on the source that is generating them. That means if there are only a few potential customers, then the calling source is finite. If there are more, say some 40 or 50, it is infinite. Or another rule is, like, a finite source exists when an arrival affects the probability of arrival of a potential future customers. Like for example, say a battery of M running machines is a finite source as far as machine repair situation is concerned. So before any machine breaks down, the calling source consists of this M potential customer. So as soon as a machine breaks down, it becomes a customer and hence cannot generate another call until it gets serviced. So unless it is repaired, it will not again call for a service. So an infinite source is said to exist when the arrival of a customer does not affect the rate of arrival of potential future customers. So that is a population or calling source. And not just that, we also have to talk about the seventh and most important element, which is the maximum size of a queue. Size of population is different and maximum size of queue is different. Sometimes only a finite number of customers are allowed to stay in the system, although the total number of customers in the population may or may not be finite. For example, a doctor is making appointments with K patients a day, K number of patients in one day. So if the number of patients asking for appointment is greater than K, they are not given the waiting token. So they are not allowed to join the queue. So therefore the size of population is infinite. Though the size of population comes under infinite, the maximum number permissible in the system currently is K. So that is the maximum size of the queue. So this is 7 most important element that can be used in order to understand the queuing model. And last but not the least, what is very, very important is, in order to understand the queuing model, because unless we understand the queuing model, we cannot try to improvise it. We have to improvise it so as to give better service and an optimum or the best possible way. So another most important entity that we have to understand is the customer's behavior. Why is customer's behavior so important? Because the customer is the one who is getting us business. So we have to understand how to manage with our queues and service stations so as to not disappoint the customer. So the different behaviors generally talked about, the customer is balking customer. So a customer is balked or reneged or is jockeying. A customer is said to be balked if the customer just saw the queue. The customer did not join the queue for service. The customer just entered the system, checked that the queue is very large and did not dare to join the queue and just left. So we lost that customer. So such customer who did not even dare to join the queue, and left the system is called a balked customer. So this customer is lost. And then a customer is said to be reneged if in case the customer joins the queue but is fed up or has some other priorities and then left the system. The customer joined the queue, but due to some reason the customer had left the queue. Customer leaves the queue and also the system. So this fellow joined the queue but left, couldn't continue with it and left. So the queue is very means the time that he has spent, he felt that it is too large, so they have withdrawn. So this customer is also lost. So we should know how much the customer is ready to wait. So they are all costly things. If there is no customer, there is no business, there is no profit, there is no life. So this is important. So is the customer, how is the customer? The customer behavior is very important. So customer is said to be reneged if the customer joined but could not continue with, left the queue and the system. And another customer is, the customer is said to be jockeying if this customer is shuffling from queues. Means this fellow is in one queue, felt that the other queue is moving quickly, so immediately joins that queue. Again that queue when he feels that is also slow, then he will shift to some other queue. So this behavior of the customer is called as jockeying. The customer is said to be jockeying. So this is another very important element in understanding the queuing model. The notations and symbols used in queuing model is taken from the Kendall. Kendall is a person who had introduced a set of notations which have become standard in the literature of the queuing models. So this person had given us the notations in 1951. A general queuing system, the notation is also called by his name, Kendall's notation for queuing model. This is considered a standard. So a general queuing system is denoted by A/B/C colon D/E, where A is the probability distribution of inter-arrival time, B is the probability distribution of the service time, C is the number of servers in the system, D is the maximum number of customers allowed in the system, and E is the queue discipline or the service discipline. Means whether it is first in first out or last in first out or random or priority, that. So that is E. So in addition, the size of population, as we have discussed in previous session, it's important for certain types of queuing problems. Like, so although not explicitly mentioned in Kendall's notation, we have to know that. We have to also keep in mind the population, the size of population. So traditionally, the exponential distribution that is used in queuing problems is denoted by capital M. Capital M is used for denoting the exponential distribution. Means, for example, if the queuing model is defined as capital M/1 is to say infinity / FIFO. This is I'm just giving an example. So that means the probability distribution of inter-arrival time is exponential distribution. This is this M/M/1. This first M is A, which is the probability distribution of inter-arrival time. The second M is the B, this B, which is the probability distribution of the service time, and this 1 indicates that C, which is the number of servers in the system, and infinity is what? The maximum number of customers that are allowed in the system, that is D. And FIFO is nothing but the queue discipline. It is a first come first served, first in first out. So this is one example of how a queuing model is defined using the Kendall notation. So this order is very important. You cannot write C/A/B or something like that. It is exactly A, B, C colon D and E. A is first about the inter-arrival time, then comes the service time, then the number of servers, then the maximum customers allowed in the system, and then the service discipline or the queue discipline. So this is called as a Kendall notation. And in general, the behavior of a queuing system will depend upon time. It depends on the time. So, such a system which is time dependent is said to be in a transient state. A system which is time dependent is called a transient system, which is said to be in a transient state. So this usually occurs at an early stage of formation of queues, where its behavior is mostly dependent upon the initial conditions. Alright, so when you are the first customer, your behavior will be different than going at the end where already there are many queues. That is what we mean by this. So when sufficient time has lapsed since the beginning of operation, so mathematically, as time approaches to infinity, say, then the behavior of the system may become independent of time. So such a system is said to be in a steady state. Transient state is in the beginning of operation, and steady state is approached when t tends to infinity. So that is a steady state, means the system is independent of time. In transient, the system is time dependent. So we will study only the steady state queuing problems.
Thanks for watching. If this video was of help to you, please like it and share it with your friends. And don't forget to subscribe to our channel.